Hello, Facebook. I'm Evan Deshefsky, features editor with PCMag.com. Welcome to the Convo. This is our Facebook Live series where we talk about talk to the biggest names in tech, science, and geekdom to see the big trends that are going to be affecting all of us real soon. And we don't get much bigger than today's topic. Today's guest is theoretical physicist Sean Carroll. We're going to talk about his new book, The Big Picture. You got that, Cambot? And his new book is about how the universe really works on the biggest and the smallest scales. But perhaps more importantly, it's about what we should do with all that information. So if you're interested in the big questions, this new book and interview are going to be for you. Okay, so Dr. Carroll, thank you so much for being here.
Sure, thanks very much for having me.
Okay, and also I want to say that if you have any questions about cosmology, quantum physics, or any really advanced science topics, or big kind of ethical, moral, philosophical things, that's what this book is about. That's what we're going to be talking about. So drop your questions in the comments, and Social Pete will read them later in the show. So, Dr. Carroll, first I want to say that I really, really loved your book. I read a lot of science books, and a lot of them kind of don't explain the big things that well. They're kind of mounted, but this is actually a really good book. I'd really recommend to anybody who's interested in these kind of big science topics. It seems to be about two minds. The first one is that you show how everything we know as reality is kind of false. It's kind of an illusion. But you also say that these illusions are kind of useful. So I guess the question I want to ask you is, what's the meaning of life?
You know, I had the subtitle that makes it sound very grandiose on the origins of life, meaning, and the universe itself. But I'm quick to point out I don't actually know the origins of life, meaning, or the universe itself. We talk about them, so it's on those things. I think we have a very good framework with which to discuss this kind of question. I don't like to use the word illusion, actually. I think that there's many layers of reality that are all real. When you talk about the air being, having a temperature and having a density, even though it's made of molecules and atoms, those temperatures and densities are very real. And I would say the same thing about human choice or morality or consciousness.
Now, reading the book, there's some things that actually stuck out for me. One is that you say the Big Bang was, quote, most likely not real. What does that mean?
Well, we talk about the Big Bang, the singularity, the beginning of the universe, 13.8 billion years ago. But we get there by extrapolating our best current theories, Einstein's theory of general relativity, the curvature of space-time is what we perceive as gravity, all the way back to a point of infinite density and space-time curvature. But that's where you shouldn't trust the theory. General relativity isn't the final answer. It does not take into account quantum mechanics, for example. So general relativity predicts the existence of the Big Bang, but that's exactly where we shouldn't be trusting general relativity's predictions. So physics is trying to move beyond that, to try to understand better what happens at that mysterious moment.
I think, further to what you were just saying, is that you also say in the book that scientists never actually prove anything. So do we actually not know anything?
No, there's a difference, right? And I think this is a crucial point. That's a very good question. We can know things without proving them. What we mean by know is not with 100% confidence. When you prove that 2 + 2 = 4, you know it with 100% confidence. When you demonstrate that the universe is expanding or that we evolved from single-cell organisms billions of years ago, this is not 100% true, but it's 99.99999% true. You become confident enough that you call it knowledge and you move on with your life, even though if new data came along tomorrow that caused you to change your mind, you should be open to making that change.
I just want to remind people at home, if you've always had a question you've always wanted to ask a theoretical physicist, now's your chance. Drop it in the comments. Now, you also say in the book, you make reference to how the whole universe can be explained in a cup of coffee. What does that mean?
Well, one of the mysterious things about the universe is why it's so complex, why we look around us and we see not only people and animals and plants, these very, very complex living organisms, but this beautiful picture of galaxies and stars in the complex cosmos today. Because the universe started out very simple. And it also started out low entropy, very, very organized. And the whole history of the universe is just a story of the universe becoming more and more disorganized. So how did it become complex? And I use the cup of coffee as an example of how complexity very naturally arises as the universe becomes more disorderly. When you mix cream into coffee, At the beginning, it's very simple. All the cream is on the top, all the coffee is on the bottom. At the end, it's very simple. Everything is mixed together. It's in between, when you're putting your spoon in there and the tendrils of the cream and the coffee are mixing up with each other, that's when it looks complex. And you and I are those tendrils, those temporary manifestations of complex structures as the universe goes from simple to simple again in the future.
Facebook, I see you have some questions. Pete, what you got?
So someone is asking about the black box information paradox, which is, it's basically if information gets trapped in a black hole, it gets just eradicated, I guess. And their question is, what if the reverse happens? What if a black hole collapses? Do you think that the information could be regained?
Interesting.
This is a good question, a little bit complex one. Is the black hole information paradox is that we think in physics information is conserved. If you knew exactly what the universe was doing at one moment in time, you could know exactly what it would be doing at some future moment, given the laws of physics. Black holes are apparently a puzzle there, because you throw a book into a black hole, the black hole evaporates away, we have no way of reconstructing what was in the book. Many physicists, most of us in fact, believe that somehow there is a way, somehow that information does get out, we just don't know yet. The specific question being asked is one I can't quite answer, because black holes can't collapse. Black holes are as small as they can be. If you put anything extra into a black hole, it always grows bigger, because the size of a black hole grows as its energy or mass increases.
Now, another thing you say in the book, and I think something I'm actually going to give you a little bit of pushback on, is you say that there's probably not life after death, but it's probably a good thing. I respectfully disagree, but go ahead.
I don't even necessarily say it's a good thing. I just say it's true, right?
Okay,
In fact, one of the things that I sort of wish were not true about the universe is the whole life after death thing. You and I are made of atoms and molecules and particles obeying the laws of physics, and there's no place for the information about who we are, our memories, our aspirations, to go once we die. We have very explicit experiments, unfortunate and otherwise, with people who've suffered brain damage, and that changes who they are. When your brain changes, like when you die, you change. I wish that I could live, maybe not forever, because forever is a long time, but a few 100,000 years, I think I could definitely keep myself interested for.
Believer in the singularity, that we can upload our brains, or hogwash?
I think it's possible in principle. I think that we're nowhere close in practice, and I think it's going to be a very different thing. One of the things we've learned from modern research is that who we are depends not only on our brains, but also on our bodies. If you put a brain with all, an exact copy of your brain and all of its neurons into a computer program, will it get hungry? Will it get tired? None of these things are very obvious at all. We might end up with a very different kind of person in that case.
Facebook, I see you have some questions. Take us to somewhere maybe not such a bummer, if you can, Pete.
So there's a controversial theory that the reality is just, or the universe is just a giant hologram. Is that something that you subscribe to?
I think it's an interesting possibility that we're definitely investigating. This comes again from the black hole information paradox. When you think about black holes, it turns out Stephen Hawking, back in the 1970s, showed us that the amount of information in a black hole is not proportional to the volume inside. It's proportional to the area of the boundary, the event horizon of the black hole. Somehow, that might mean that all of the information in the universe can be thought of as living on some two-dimensional sheet, like a hologram that the universe projects to make our three-dimensional reality. There are very intriguing examples where this seems to be the case, but I think that no one would say that we understand it well enough to say for sure right now.
Just because I now have a chance to talk to a theoretical physicist. So one of the questions I've always had, or at least been curious about, was now in Hollywood, they make a lot of use of extra dimensions and creatures from other dimensions. And I've read about how there are dimensions that we possibly can't see or experience as humans. Now, is that actually a proven fact, or a fact that we go with as a truth, that there are dimensions that we can't tell, or is that just stuff that works well on a blackboard somewhere?
Yeah, so it's certainly not proven. It's a speculation. We don't have any direct evidence for the existence of extra dimensions. But also, physicists use the word dimension to mean something very different than Hollywood uses it to. When Doctor Strange comes out later this year, you will hear about the dark dimension. A dimension is a place you go visit. Oh, I'm going to go to the dark dimension and I'm going to come back. For a physicist, a dimension is a direction, right? Up, down, left, right, forward, backward. Those are dimensions. So when we talk about extra dimensions of space, it's not a place you could go, it's a direction you could move in. Now, obviously, we don't see any such extra dimensions. So to make it consistent with what we observe, they would have to be wrapped up into very, very, very tiny little regions of space. Right now, it's wholly speculative, but we're keeping an open mind.
Gotcha. So you heard it here first. Doctor Strange is all fake. So Facebook, what else you got?
Is the concept of time actually an illusion?
No. I mean, obviously not. When someone says, show up at 8 o'clock for dinner, you don't go, my goodness, how could I do that? This is all just an illusion. You know what that means. You can use it. I think that we're a little bit too quick to apply the word illusion to what we really mean as emergent or not fundamental. If you want to know, does time play an absolutely crucial role in the most fundamental laws of physics? The answer is we don't know. We're exploring different options where time is fundamental or may not be fundamental. But it's certainly not an illusion. Time is definitely real. We all know what it means when we say this TV show is going to last 1 hour long.
Now, when it comes to quantum physics, and one of the weirdest things that's come out of that is the multiverse, which I believe you said you're at least have an open mind to, if not a fan of that theory. But maybe explain what that is briefly and what implications it would have, and do we have any way of testing that?
Yeah, I'm a fan, and there's sort of many different versions of the multiverse idea. Some are more well-established than others. None of them are essentially perfectly established. All of them are up for grabs. Two in particular are quite popular. One is called the cosmological multiverse. And that's really a fancy way of saying that very, very, very far away, conditions in our universe could be very, very different. So we call it a different universe, even though it's just far away from us. And by far away, I mean way outside what we could ever possibly observe, right? Light moves at a finite speed. We can't see infinitely far away. So there could be just regions of space out there where things are very different. The laws of physics are different. The number of dimensions of space could even be different. The other idea is in quantum mechanics, we have what's called the many worlds theory. When you see a quantum event, like a nucleus of a radioactive atom decaying or something like that, we have this weird thing that quantum mechanics only gives us the probability that it's going to happen. It doesn't say for definitely sure what will happen. So one very attractive idea that I personally think is very, very likely to be true is that when this quantum event is observed, every possible observational outcome comes true, but in a different universe, in a different world. That seems to be the most straightforward way of reading what the equations are telling us. A lot of people resisted this because they don't like to think of that happening.
Sure. Facebook, what else you got?
Can energy be created or destroyed, or is it static in the universe?
Actually, that's a surprisingly good question. And I say it's surprisingly good because most physicists would just say, no, it cannot be created or destroyed. Energy is constant. But in fact, if you are familiar with cosmology and the expansion of the universe and gravity more generally, you realize this is a more subtle question than it used to be. In an expanding universe, or whenever space-time curvature really matters to us, there's more than one way of defining the energy. Some ways the energy is conserved, but it's also kind of trivial. It's just always zero. Every situation has zero energy, so it's kind of uninteresting, really. Another way of defining energy, sort of the more conventional way, is not conserved. As the universe gets bigger, the amount of energy in some kinds of things goes down, other kinds of things could go up, and they don't have to cancel. So I think that the simplest answer is just that on cosmological scales, energy is just not conserved. But here on Earth, it is to a very, very, very good accuracy.
Now, talking about the possibility that the universe is actually a hologram. Now, I guess about a year ago, some people actually did an experiment to see if they could prove that, or at least get more information about it. And as far as I know, it did not. They didn't get anything definitive out of it. So, what other big experiments are coming down the line, maybe within the next year or two, that might actually give us some real insights?
Yeah, it can be frustrating sometimes, the lack of direct experimental test of these ideas. Partly that's just because, the ideas are very speculative and they're running far ahead of our ability to actually pin them down. So it's not that we've ruled out the holographic principle or anything like that. It's just that the principle is too vague to yet put it to a test. We're all hoping to make it much more specific and testable. Meanwhile, we have many, many experiments that are testing things that are more well established. The Large Hadron Collider that discovered the Higgs boson in 2012 took a bit of a break for an upgrade and is now running again. We're hoping that will discover new particles. Of course, we've recently discovered gravitational waves at LIGO, and we're hoping to discover many, many more gravitational waves than that. We're probably the most exciting thing that hasn't quite paid off yet is the search for a direct detection of dark matter. We think that most of the matter in the universe is dark, which means not only that we can't see it, but it's something that we've never seen in any laboratory here on Earth. But it's most of the stuff in the universe. So we think that's just because it interacts very, very weakly. Dark matter particles are flying through your body right now, but they just don't even bump into you, so you don't notice. So we're building giant, ultra-sensitive detectors underneath the ground, hoping to directly see that dark matter.
Cool. Facebook, what you got?
Is time compressed by the gravity of a black hole? And if so, is there a way to calculate the effect of the perception of the passage of time by an individual if they could exist on the event horizon of the black hole?
These are good questions. You people are obviously hanging out on the wrong street corners if you even are asking these questions. And the answer is yes. Actually, this was Einstein's great insight, which is that different people moving in different ways through the world experience different amounts of time. Time is relative. It is not absolute. So the twin paradox, if you have two people born at the same time, one goes out near the speed of light in a rocket ship and comes back near the speed of light. The one who moves out and back will come back, they'll meet each other again. The one who went on a trip will be much younger, will have experienced less time. Roughly speaking, the more you move through space, the less time you experience. And the same thing happens near a black hole. If you go very, very close to the event horizon of a black hole and you come back, you will have experienced very, very little time. And I'm sure this will be a major plot point when Disney remakes the Black Hole movie. I think that's going to be a fun little thing to think about.
Definitely. Now, string theory, that was a big popular theory, or at least I heard a lot about it about 10, 15 years ago. Is that still a favorite among physicists? How's that doing these days?
Yeah, string theory is definitely a favorite, although there's good news and bad news. The bad news is we haven't really been able to, once again, develop the theory well enough to really answer the questions we had when the theory was first generating so much excitement in the 80s and 90s. Namely, is it a theory of everything? Is it a quantum theory of gravity? Does it fulfill Einstein's goal of unifying everything we know? As far as that's concerned, we're just not sure. We just haven't been able to answer those questions. But meanwhile, we've learned a lot about the fundamental structure, both of string theory and about other theories of physics, of particle physics and quantum field theory. So we're now using string theory to think about nuclear physics and materials physics and atomic physics. So it's sort of the barriers have come down a little bit, where string theory is just part of physics. It's not sort of a separate realm all by itself.
Cool. Facebook, you have a question. What you got?
Is there a difference between string theory and M theory?
There's a little bit of a difference, but neither one are very well defined, so I wouldn't get very hung up about it. This refers to a fantastic discovery that was made 20 years ago now by a bunch of people, including Ed Witten at the Institute for Advanced Study. They used to think in the 1980s that one of the great things about string theory was that there were only 5 different kinds of string theory. That's opposed to, theories of particle physics where there are an infinite number of different kinds. And that was pretty good, only 5 different kinds. But what we discovered in 1996, 20 years ago, is that in fact, even these 5 kinds of string theory are related to each other. They're just different versions of the same underlying theory. And there's another theory in 11 dimensions that is also related to them. And the whole shebang is descended from what we call M theory. So M theory is a theory we don't even know yet. It's a theory that when you look at it in certain ways, it looks like a string theory of one type or looks like a string theory of another type. So I would say that M theory is the theory from which string theory and everything else is supposed to be descended.
when it comes to artificial intelligence, there seems to be two camps. There's people like Elon Musk who are, actively like funding think tanks about why we should be scared of AI. And there's like the Google guys who think that it's going to be the savior of humanity. Is AI something we should fear or be hopeful about?
I agree with both camps very firmly. I think we should optimistically move forward while being very, very cautious. I mean, I don't know if fearful is the right word, but it's easy to imagine scenarios where things would go dramatically wrong. Just because you can doesn't mean you should. So I think that it's very, very smart, Elon and other people who are thinking hard about the dangers of artificial intelligence. And it's exactly the same story as the dangers of contact with extraterrestrial life. Any advanced alien civilization is likely to be enormously more advanced than us. It would be very, very exciting and interesting to contact them. But history shows that we would be smushed if we actually contacted them. So maybe we want to be a little bit careful. I think it just makes sense not to let our techno-utopianism get away with us. We can both try to make advances in these fronts and be properly cautious about them at the same time.
And speaking of techno-utopianism, I kind of sometimes gear towards that frame of mind. But I would at least say I'm a techno-optimist. I think science, technology has done wonders for humanity. I would say also that over at least the last year, there's been a lot of horrible things happening in the world. Are you an optimist or are you a pessimist?
I'm a cautious optimist, I think. I think that it's very, very hard to tell what's going to happen in the future because we're going to be confronted with technologies that we don't have right now. I mean, I think that the majority of the shocking developments that will happen over the next 100 years will come in biology and at the human-machine interface. We're going to become, more and more cybernetic. We're going to, use machines not only to help us, but to be part of us in interesting ways. I do believe there will be artificial intelligence that we'll be talking to and dealing with in interesting ways. We could do things like cure aging. We could make it, you just go in every year to get a little tune-up and you come out biologically just as young as you were a year ago. And there's no reason to think that human beings couldn't live for thousands of years. And that's going to be a dramatic change. We're certainly going to be able to edit the DNA of children that we have and things like that. And none of these things are things that we've really thought about, dealt with, or even have the tools to think about very accurately right now. So it's both scary and exciting at the same time. It's up to us to be responsible in how we deal with it.
Okay, we're running out of time, but maybe we can get one more Facebook question in there. Pete, what you got?
Is it possible that we are living in a black hole?
Roughly speaking, no. I mean, anything is possible. That's why I always say roughly speaking. We never know things for 100% certainty. But it's more like we live in a white hole. A white hole is the hypothetical reverse of a black hole. A black hole is something you can fall into but never come out. A white hole is something that things leave but can't fall into. In a black hole, if you fall into a black hole, what that means is that in some finite amount of time, you're going to crunch into a singularity. We don't think the universe is like that. We think the universe is going to expand and get more and more dilute forever. So it's not very black hole-like at all in that sense. But there is a singularity, according to classical general relativity, in the past, namely the Big Bang. I mean, we hope to replace that with some better quantum theory of gravity. But that's what you expect in the time reverse of a black hole, aka a white hole. So the fact that we have a singularity in the past and not the future means that a black hole by itself is not a very good model for the universe in which we live.
Great. Well, I think that's actually about all the time we have. I could keep this conversation going for another few hours. My bosses wouldn't like that so much, so we have to wrap it up. So I want to say thank you, Dr. Carroll. His new book is The Big Picture. It's an excellent read. I'd say pick it up. Thank you to Social Pete. Thank you to everyone who has participated on Facebook. Be good to each other, and peace. Dr. Carroll, thank you so much.
Thanks much, guys.
Have a good one.
All right.